Hi everyone. So I will talk to you about deriving theorems in implicational linear logic declaratively, and this is joined to work with Valeria De Paiva. I will start with an overview. So our goals are to derive a theorem prover for a decidable fragment of linear logic, and that's implicational propositional intuitionistic linear logic. We'll abbreviate it IPL for now, and we would like to do that partly to be able to enable training neural networks to find the proof terms once we have enough data generated by having a theorem generator for this particular logic. So how to generate all theorems of a given size, that's then the problem that we would like to solve. And the solution that I will explain here is to derive an efficient algorithm that would require a low polynomial effort per generated theorem, and that despite of the fact that theorem proving for this particular logic is reasonably hard, we will actually use a trick here. We will rely on the Curry-Howard isomorphism, and we will focus on generating simply typed lambda terms in normal form, which would serve as proof terms for our logic via the bridge that crosses from lambda terms to formulas. And as a set of outcomes that we will have here is an implicational intuitionistic logic prover that's spatialized for IPL formulas, and of course a data set for training neural networks with a few preliminary results on that with very high success rate with a sec-to-sec encoded LSTM neural network, which is not in the paper, but it's quite cool. Okay, the implicational fragment that we will be talking about, linear logic provides the ability to constrain and control the use of formulas available as premises in a proof. While propositional intuitionistic logic is already Turing complete, its implicational fragment is fortunately decidable, and in fact, polynomial algorithms exist for that. Now, polynomial algorithms for generating its theorems are useful when turned into test sets by combining the theorems and the proof terms, the lambda terms corresponding to them, describing their proofs, can be useful for testing correctness and scalability also for linear logic theorem provers. Now, if we turn them into data sets, pairs basically of the theorem and the proof term, they can be used for training deep learning networks that focus on neurosymbolic computations, and theorem proving is a prototypical example of those. So let's look a little bit into the Curry-Howard isomorphism. It's of particular interest because it describes how computations and proofs of theorems relate. In its simplest form, it connects the implicational fragment of propositional intuitionistic logic with types in a simply typed lambda calculus. Now, the bridge is easy to cross one way. A low polynomial type inference algorithm associates a type, when it exists, to a lambda term. On the other hand, crossing it the opposite side is hard. PSPACE-complete algorithm associate inhabitants to a given type expression with the resulting lambda term, typically in normal form, serving as a witness for the existence of a proof for the corresponding tautology in implicational propositional intuitionistic logic. This suggests to use combinatorial generation of lambda terms, in normal form ideally, plus type inference, which is easy, to solve some type inhabitation problems, which is hard. And this picture shows on the left implicational formula with the lollipop notation. And on the right side, we have the corresponding lambda term. So I'm using L here for lambdas and A for applications. So this is lambda x, apply lambda y, apply y to x. And that's the formula. And the integers here are numbers that correspond to distinct variables. And our lambda x, x identity application is here. And here we would see the formula that's not in a normal form, corresponding to a smaller term here. On the other hand, if the terms here are in normal form and we infer their types, then we will get a principal type that would look kind of about as big for linear logic as the formula, as we will see a bit later. So how we proceed? Well, the formula generators, and the details are in the paper, are fairly simple Prolog code that's built as a generator for binary trees of size n, counted by the Catalan numbers. That's for generating the formulas. And we label them with variables derived from set partitions. That's kind of a minimal way to use variable labels that's canonical. There is a unique representation for a given term rather than going over all the variables, taking all possible positions, which would be a little bit more. But even then, this is super exponential. We have Catalan numbers n times Bell numbers n plus 1 to count all those possible formulas. Linear lambda terms now can be generated a bit more efficiently, and we have a series of steps in the paper that show how that generation process goes. We first generate the linear skeleton Motzkin trees, binary unary trees with constraints enforcing one-to-one mapping from variables to their lambda binders. And then we generate closed linear lambda terms, so closed terms that are such that for every lambda binder exists exactly one variable that it binds, and the other way around as well. And then we focus on terms in normal form. So normal forms cannot be reduced with beta reduction anymore. There are no lambdas on the left branches of applications for them. So after a chain of refinements, we derive a compact and efficient generator for those pairs made of a linear lambda term in normal form and its type, which always exists, as all those terms are typable. Of course, that's kind of obvious because each variable, each lambda term has a single variable corresponding to it, so there is no conflict, type conflicts between two variables corresponding to the same binder. So with that, we generate quite a few terms here, about 7 billion in a few hours. We generate them together with the corresponding types. And they are theorems in this logic, IPIL, via the Curry-Howard isomorphism. And that's also a sequence. Those sequence numbers here correspond to the their code in the online encyclopedia of integer sequences, which is a very good resource for anything related to generating interesting sequences, because sometimes they correspond to a lot of other combinatorial objects. Now, our generator, after all those derivation steps, is actually very compact. It's something that given a budget and how many, how big the terms could be, that's the size of the terms, we would then decrement that budget, and this is the predecessor function that will do it step by step. Here's an example of a predecessor applied for that. And then what we will do as we go, we have two things to keep in mind. We don't want lambdas on the left branch of an application to appear. So that's why we distinguish between linear neutral terms that obey this constraint. And then we would like at the same time to enforce the constraint that for every lambda binder that we introduce here, we have exactly one variable that would take it. So that's basically the algorithm. And because this is a literate program, of course, you can try it online. The link is in the paper. So let's look at the normal form of some interesting terms here. We have a term on the left and a term on the right. And you kind of can see some similarities here, definitely similarity in size. That's the first element. And then here we would see also some similarity in size and some interesting symmetries coming up. So that's what actually would actually suggest a deeper connection. And this brings us to our eureka moment. So we have some interesting symmetries in the pictures. And now we see that we actually solve the problem of generating all IPL tautologies of size n if our predicate that we just showed you, linear type of normal form, implements a generator of the approved terms of size n. And we are lucky. We actually have a bijection, a size preserving bijection between the two. And in the paper, we detail a little bit where it comes from. But what we get out of this is that if we solve the problem of generating the lambda terms in normal form, we get pairs between lambda terms and their corresponding formulas. And well, we discussed a little bit about that, but well, in the interest of time, I will just mention that a reason why we are doing this is a long-term goal is to improve on the already known translation of intuitionistic logic into intuitionistic linear logic. And for that, we need to know more about the universe of existing linear proofs, like how many they are, their shapes, invariant properties. And this is a step forward in that direction. So among the applications, of course, the data set that we have the links in the paper and the link also here. And then those formula and proof term pairs are very good for training neural networks. And here is an example of what we get if we train them with an LSTM set-to-set neural network. We see that the accuracy curve is very good. Actually, we get very quick convergence. And we'll show you in future papers more work on that. So that's our conclusion. We found a way to generate a theorem prover for a new logic by crossing the Curry-Howard bridge one way and the other way. And that's a very reusable technique also for other similar logics that we mentioned in the paper. Thank you.